Hello and welcome everybody to Advent of Code 2023, day 21, being recorded on day 22. So I was a little bit behind with this. Last couple of days have been extremely busy, as are going to be my next few days. So this may be the last full puzzle I get done and also a full video made on. I've had a quick look at day 22 and I don't know if I'm going to be able to get it done today, and then I'll have a look at 23 and 24, but I know I don't have a lot of time over the next few days, so not sure if I'm going to get them done. I definitely want to do the day 25 puzzle because it's usually not too hard, and if I make a video on that day, it'll be my way of saying thanks and happy Christmas and happy New Year to everyone who's been following along with me for the whole month. So with that said, anyway, we have day 21 done. We're going to look at it, we're going to talk about it, and yeah, let's just jump straight in. So, day 21, step counter. So we've been following our way back down through the islands, and we've managed to catch an airship that's brought us back to the island, the farm on Island. So we've met the gardener, and the sand's coming, which is great. But in the meantime, so they have to wait for the sand to build up before they're going to be able to filter the water to send to Snow Island. So in the meantime, the elves ask you to help him with the problem. So the gardener elf basically says that he's got a certain number of steps left for the day, as in like his step counter, and he wants to know from the plot that he's standing in his garden now, how many possible plots could he get to with exactly his remaining 64 steps that he has for the day. So we're told this is something like our puzzle input. You've got the plots are the dots, hash marks are rocks that you can't walk past, and then the S is the starting point, which also counts as a plot in the logic that they've set out here. So you go through the examples, and basically what happens is he starts in one position, and from here, if you look to, so you can move up, down, left, right, so there's no diagonals. So from here, he looks around and he can see I can go up or I can go right, so there's a possibility of two different places he goes. So then, depending on whether he goes to one or either of these places, he has another set of possibilities of places he can go. So he could go back to the start, he could go up again, and then if he's on this one, so if he's here, he could have gone left or down or back to the start again. So basically what we're told to do is so that's an example. If he's taken 2 steps and he now has a possibility of 4 different places he could go to. So we're told that this will basically, he's going to take 64 steps, and at the end of the 64 steps we need to figure out how many unique places he could end up, which isn't not a terribly hard problem when you think through it. It's basically a map traversal thing, and you figure out once you get, so you just keep walking in this tree until you get to until every path that you've walked hits 64 steps, and then you can exit out and get your answer, and that'll be it. So yeah, that's about it really. Not much more complicated than that. So let's have a look at the code to do that. So this is our part 1 code, not super long. So we start off, we have our map, we have we're going to set up some starting coordinates when we find them. So we iterate through each line and each character, inserting them into the map, the character that is. When we get the S character we see in our map, we log those as our starting X and Y coordinates. And then this is basically just how we're going to traverse the map. So we're going to walk this recursively. I have a few data structures up here. I'll explain them in a second exactly what they do, but the main thing is we can pass them into our step function, which will iterate through all of the different steps recursively, and then when it returns, we can go to the depth of the steps that we want, which for the input is 64. For the example that they give us, it's only 6 steps, and then we can spit out the unique steps we have, the count of those locations, and that will give us the answer. So to look at the guts of what the recursive function does, we're involving a cache in this to try and short circuit some of it. So in this case, I decided that the cache key was going to be the X and Y coordinate, excuse me, and the number of steps it's taken us to get to that point. And yeah, if we hit that, then we're not going to, if we go to end up at that point with that number of steps, we're not going to continue. So we just return. So that'll prune down to stop us repeating all the points. Then this is just the lookup of these collections of similar variables I've used before, which just lets you go check up, down, left, and right. We pull all those out. We check them off our map values to see are they a dot or an S, which we know is a place that we can walk to. If it is, then we record the fact that it's a place that we can walk to, and we record the coordinates that we're going to go to. And then this little check in here, this step depths is a hash that's keyed on every depth. And then for every depth, it's going to have a list of all the unique nodes that you can get to from that. Or at that point, it's a list of all of the nodes that you can go to possibly. So then at the end of it, you get the unique amount of those that are in that, and then that'll give you your answer for the number of steps. So yeah, we update our cache once we've updated these values, and then we'll return if we've reached our depth. So if we don't need to take any more steps. If we haven't reached our depth, we take another step in this recursion. So we know there's 4 possible steps we can take, and then this if check up here relates back to up here where we built this data structure. It'll be true for the ones that are valid. So if there's a dot, and if there's a hash, then it'll be an invalid one, so we won't take that step. And then we just pass in the relevant data, and we just keep going with that. And yeah, we keep churning with that, and then that will eventually spit us out our answer. Yeah, so nothing hugely complicated there. But yeah, that's basically it. So if we run that on the, so this is 21, 1 on the sample, should spit out 16, which is the correct answer. And then we can run it for our input, and this will also spit out the right answer, yeah, 2660. So that's the first part, which is pretty straightforward, pretty simple, nothing crazy complicated there. It is the second part where things kick off a little bit. So let's go and have a look at the second part. So for part 2, they tell you that the number of steps is completely wrong. And in fact, the number of steps is way bigger. So it's this, the number of steps he wants to take is actually 26 million, blah, 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 blah. So that's a lot. Or sorry, is that 26 billion? Is that a billion? Yeah, I don't know. Numbers confuse me. Anyway, it's a big number. And what we're told is that our map actually repeats infinitely in all directions. So it's an exact copy of this map heading out in all directions. And that's actually what we're doing. So we now have to check way more steps, and we have this infinitely repeating map that we also have to be able to keep track of. So effectively, we're told it's the exact same type of problem. We're trying to find the max combination of steps, or the maximum combination based on the number of steps we've taken. We're given the number of steps to test for. So in theory, we could just iterate until we find it, but that will take a very, 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 very long time. So we don't want to do that. We want to do something else instead. But the first thing we need to also be able to do is we need to be able to simulate a certain number of steps. So this is another type of pattern problem where we just need to simulate to a certain amount, and then we'll be able to get our answer. But the certain amount we have to simulate to is going to be greater than one single map. So we're going to have a way of simulating across an extended map without actually physically extending it. I guess you could, because I don't think you need to go quite that far that you wouldn't be able to fit it into memory. But I came up with a relatively clever way to do it, which I think I saw a lot of other people doing as well. But then there's a little mental leap you have to make, and it's not obvious at all exactly how it works or why it works, but I'll do my best to explain it. Anyway, let's have a look at the code. So the code is mostly the same. Same kind of parsing, same setup, basically the same stepping function. There's just one trick really, to be able to allow us to expand outside the bounds of our map. So if we scroll down to our step function here, we have the same caching mechanism, but we have this new thing down here, this new function, which is I've called mod translate. And so basically what this is doing is it'll take the XY coordinate, any XY coordinate that we give it, and it'll translate it with a mod operation so that it always falls back inside the main grid again. Because we're told that the map repeats infinitely exact copies of itself in all directions, you don't need to worry about there being any like buffers in between. So if I go off the edge of one map, it effectively loops back around to the start of the other map. So I can do that with this mod operation, because we talked about this before, but if you take any number, mod another number, will always give you a value between 0 and the other number's value, the second number's value. So we can use that to basically loop our map over and over and over again. The only thing that we need to do with the way our data set is set up is that we need to do that when we address the map to see what value we have in the map. So that's why I have these key values here, which are what we use to check our map are translated, but nothing else is translated. So the cache values, they're not translated, and the values that we store in the step depths lookup, they're not translated either, because they need to be unique. But what doesn't need to be unique is just looking up the map to see what the structure of the map is at that point. That's the bit that we can do the translation on. So once you do that, this problem is fine. It took me a little bit of a while to get this right. I was like banging my head off this for a little bit, but once you get it right, it's fine and it works. But then the real trick becomes figuring out the pattern. So you can use this code exactly as it is to simulate the sample, and you can brute force the answers for the sample and get the correct answer, so we know it'll work. But to get to your actual answer for the puzzle, you need to notice a pattern in the input that isn't present in the example. So people have given out before about looking at your inputs and trying to find a pattern in them that's some emerging behavior that isn't in the examples. Which sometimes I'm like, well, sometimes the examples do actually show you certain pattern that can give you a hint. But in this case, the example doesn't have any pattern in it that's useful for this, except for you have to look at the input to get the pattern, which is quite challenging. If you didn't spot it, this problem would be a hell of a lot harder. So the real trick is that the relationship between the number of steps taken and the value of the number of combinations of steps possible at that step count is a quadratic. And that's it. So once you notice that, then you just need a little bit of maths to be able to arrive at the correct answer. So for that, and then this is another part where you need to have a bit of a mental leap to get it right. So that's effectively this maths down here. So this is just the form of a quadratic equation. But all of these numbers now are, and so yeah, you don't need to worry about these. This is a standard formula. This thing here is, which is called the 3-point formula. So if you have 3 points that are all on the same quadratic, you can derive the formula for that quadratic from those 3 points, which is fine. We can do that. So you don't need to worry about too much where that comes from. Then that will feed us into this quadratic. But figuring out what 3 points to use, that's the trick. So the pattern, which is basically where it repeats, you can figure out. And where it repeats is there's some initial state. So the first square has some initial state that kind of expands out. And then beyond that, there are basically blocks of the width of the, the width of the input that end up forming like a diamond pattern. And then that expands out and expands out and expands out. And it's the same repeating pattern is expanding out the whole way. So what that becomes is, so 65, because our input is 131, So we start in the center of that. So if we go 65 out, we've reached the edge of that input. And then it's 131 and 131 after that. And those are the 3 points that we need to use for our quadratic. So that's 65, 196, 327. So if you simulate these, you can get these values. So that's effectively what all this does up here. So this is hard coded just to give me the values I want. But this part up here, all it does is it runs the simulation up to 350. And then it dumps out all of the values that it got for those steps. And then I've just pulled them out here, which is what these values are. And then you plug all that into the formula, and that gives you your answer. And it's not great. This is far from a generic solution. It works. It gives you the right answer. But yeah, I mean, I'm not super happy with the way that I arrived at this and how that I had to do some kind of manual steps to be able to plug it all in and make it work. But yeah, I'm not going to run it either because it takes a little bit of time to run. It's quite slow, so I don't want to sit and wait for it. And also, this won't even run on the sample because all these numbers are specifically picked out just to work on the main input. So it's not even a generic solution for the samples. This part here up to here will spit out the correct answers for the sample, but I mean, who cares because they don't actually matter. Yeah, I know, Kat, right? That's tragic. So yeah, that's kind of it for 21. Not my favorite puzzle we've had. Definitely leaves a little bit to be desired. But yeah, so that is it for today. As I said, I'm not sure what my time's going to be like over the next couple of days to try and get puzzles done and videos out. But hopefully I'll be back with one last video at the very least on Christmas Day. If not, maybe one of the days before, if it's an easy enough puzzle, which I doubt any of them will be for the last few days. If I get one that I look at and I think I can do it, I'll try and get it done and get a video out. But if not, I'll hopefully see all you guys on Christmas Day at the very latest. So good luck with the rest of the puzzles if you're attempting them, and I will see you guys soon.